Hi everyone, my name is Gavrilov and I'm an application security engineer with Innostage. And today I'd like to talk to you about my research, which was devoted to ways to bypass security tools based on eBPF. So the agenda is as follows. For starters, I will give you a brief overview of the eBPF because I don't think everyone knows what that is. Then we'll try to understand how come eBPF tools are used for security purposes, what are the strengths and weaknesses, and then I will share with you my assumptions on how to bypass eBPF tools or force them not to log our actions. Then I'll show you how eBPF-based tools actually work, whether my assumptions were right. Then we will summarize everything. Let's move on to the main part of the agenda. It's common knowledge that advanced operating systems support two-layer privilege allocation, and that is the privileged mode when all the apps have full access to the hardware, and that's the kernel of the operating system and the drivers that you have to get access to. So we call it kernel space. And there is non-privileged mode, or the user space, and this is where we run our browsers, code editors, and so on and so forth. And since software from user space need to get access to the hardware, for instance, to write something in the file, store the process, and so on and so forth, they send requests to the kernel space, and they use a special syscalls as they're called. System calls, just like any API, any program interface, activate other functions of the cell, of the kernel, and the eBPF allows us to register all the usual functions of the kernel, and they could be of different types, and we can either register them or impact the functions if we're not satisfied with option A. Now, there are some user space programs. First and foremost, it is necessary to load them into the kernel, and we can use GUI or web apps to this effect. Different types of the programs executed in user space and kernel space exchange data with the help of maps. For instance, the user part can write the policies for the executors and for them to know what events to detect, while the kernel part writes all the events detected while monitoring the kernel functions, and it is displayed by the user part. The kernel space profiling is nothing new, and the eBPF just allows us to avoid major pain points. Since all the executors are based on the virtual machine, there is a very low probability of damaging the kernel space. Before eBPF, we had to use kernel extensions, and if some bug was found there, not only the extension would crash, but the entire kernel would go into the kernel panic mode. And these executors are totally independent from the kernel. All you need to do is compile them just once, and it will hold true for all the other kernel versions. Otherwise, you would have had to compile separate executors for different kernel versions, because the interface structure would change with the version. And the eBPF could not but be used for security purposes. Currently, lots of technologies use it for monitoring and protecting the infrastructure. And this slide lists some of the open source tools that use eBPF under the hood. The exhaustive list, the full list, and the description of the tools is something that you can find if you scan the QR code at the right-hand bottom corner. eBPF is also used by commercial products, not just open source products. And you can ask any vendor what they use to protect the Kuber, and they would probably tell you, well, it's a high probability that they use eBPF-based tools for ensuring security. So I think it would be of interest to vendors to learn the outcomes of the research. Anyway, when I realized the way, when I got familiar with the technology and the way it works, I realized that many kernels can track the functions. So I decided to do research, and let me start by identifying strengths and weaknesses of this technology for security purposes. As mentioned before, one of the strengths is the detailed monitoring with information about context, regardless of what the kernel logs and what other tools logs. We can identify the data structure, the fields of which are of interest to us, and that allows us to restore the events and the information. Another strength is that it ensures synchronous event blocking if you don't like one or other event. In other words, you initiate a function, you initiate the executor, and then you make a decision on whether to block an event or not. In other words, the event is blocked before you go into the logic of the kernel function, and that removes any delta time for an attacker to carry out his attack. And last but not least, it's performance. Since everything is done within the kernel, you don't need to copy that to the user space and then process it. As for the weaknesses, they include the following. Maps have limited sizes, and they cannot be read simultaneously. The latest version of the Linux kernel has about 1 million instructions, but before that it was about 492,000 instructions. Not every event can be detected through a kernel function. The maps cannot send external network requests for us to make a decision, and so on. In addition to that, these maps are integrated into protected service, which have a limited service life, and we don't want our security to eat up much of the flash memory. Sorry, random access memory. Not every event can be detected through a kernel function, and they cannot be read simultaneously. If the map events registered by the kernel part is overflowing, then it will not be able to write anything on top without damaging the previous events if the user part did not have a chance to read it. So you either do not register if the maps overflow, or you just rewrite the maps. Next one, you don't have to initiate exec VE to launch some function, especially when the buffer overflows. So how can we use the weaknesses to bypass the detection? We can play around with big data, since since the memory is limited, then when you launch a large file, or if you have a large number of arguments, the map will not register some of the data. You can overwrite maps, and that means that the events will be lost and will not be passed on to the security administrator. You can skip the use of kernel function, and if your eBPF-based tool is based on a whitelist abusing, you can perform allowed actions for malicious purposes. As mentioned, maps are limited, and that means that they don't execute a very complicated technique to identify malicious actions. For instance, if a process is allowed to read the process configuration, but it's only do that on startup. If you read the config an hour later, the map does not check the whitelist actions, and this is a way to hide our actions. Some of my guesses are based on the fact that the security tools are implemented in a wrong way. For instance, they monitor just part of the functions or wrong functions. For instance, in Linux, there are about 4 to 6 system activations just to read a file. And if your tool identifies just half of them, you can use the other half to hide your actions. Built-in rules for monitoring might not be implemented correctly, and that their logic might contain a vulnerability that we can abuse to bypass the rules. And my experience forced me towards an idea that invalid characters in registered events are not being handled correctly. Well, by the way of guinea pigs, I selected two tools, Tetragon and Cube Armor. They're relevant, they're actively supported. That's why they are on the list of my research. And I also used some of the self-developed software tools. You will see some of them in the screenshots in my presentation. I will give you every detail on what they are used for and what they do. They would allow me to run syscalls and launch lots of processes to overflow maps, as well as use various invalid characters. And I used some open source software because it was easier for me to copy and paste them. Right, so let's deep dive into Tetragon. It's an eBPF based solution. They position it as an observability and runtime enforcement solution for servers. So this solution can protect Linux-based servers as well as containers and Kubernetes. And it only, by default, it registers the startup and the stop. Everything else should be described by the policy specifying the kernel functions that will be monitored. Let's look into the tracing policy. The TCP Connect connection is registered with the TCP Connect. When you syscall this function, the first argument that you see is the socket, and then if the connection complies with our filter 127.0.0.1/8 or 192.168.00/16, then it will be registered. This is a syscall for right. If nothing happens, we'll just kill it off without using any filters. Let's move on to bypassing this tool. This is the configuration that I used in my research. This is the Kubernetes with 3 nodes, the Tetragon itself, and some of the commands I used to get logs from Tetragon. Let's start with a simple thing. That's big data transmission during the startup. This is a sequence of 0 to 9. Repeated over and over again, and as you can see, Tetragon does not register such a large argument, and just a third of 100,000 symbols in the argument are registered. So we can inject something there, and Tetragon will not register it. The same holds true for similar arguments. After you launch 7,000 large arguments, and Tetragon does not registers the main part, and it just disappears. In this particular case, Tetragon failed to register the very fact of opening the file. It shows the way it tried to register the launch of my tool, an affiliate bitcat process with a large number of arguments. I cut them off to fit it into the slide. LDSO cache files were opened, so it did not register the very fact of opening the file, so we killed 2 birds with a stone. First, we hid our intent to read the file, and we hid the very fact of opening and reading the file. Large binary path is not registered by Tetragon either, and I used my own tool to launch echo hello with 1009 characters, and starting from symbol 1010, the Tetragon failed to register it, although in Linux the maximum file name is 496 symbols, and it might seem like a child's play to you, but if you can deploy your container into the keyboard of the victim, you can position your hack tools after 1,010 symbols, and Tetragon will not register it. These are the outcomes of 3 of my researchers when I tried to launch thousands of processes, 8 kernels each, and the bold parts are the registered events, while the non-bold parts are those that Tetragon did not register. And for an attacker, it's not a stable approach, because it depends on various parameters such as the number of processes being executed, the number of registrations in the maps, and the policies that you specified. In other words, in some cases you will be able to hide directions, and in some cases you won't. The third attempt considerably differs from the first 2, and basically all the events have been registered. Now let's move on to the coding. I executed my own tool, self-developed tool, and all the hex symbols have been converted into UTF-8. The Tetragon registers the fact that I launched the tool, and it also registered the bin echo that displays hello. I modified the payload, and I added invalid UTF-8 characters. That's UTF between A2 and CE. And the invalid character is displayed while the tetragon only registers the start and the stop of my process. So once again we managed to bypass tetragon. If we use a special tool, a special tetragon tool, which is called Tetra, to analyze logs, we'll see that it contains an entry saying that invalid ETF8 line was transmitted. That's why this event was not registered. And I told the Tetragon team about this vulnerability. They already fixed it. So if you use Tetragon in your company to protect your Kubernetes or Linux hosts, you can download an updated version. And since in Tetragon by default we don't have any rules for identifying malicious actions, we cannot assume, we cannot make any assumptions about the correctness. So I suggest we try to take a look at the way to describe the rules in Tetragon. And that's like shooting yourself in the foot. Let's say we want to execute bin echo. How can we monitor it? We can trace it by using 6 exact SVE.
И сравниваем его с интересующим нас значением. Пробуем запустить это через bash.
Then we try to use the bash to execute it in Tetragon registers our syscall. Then I try to do the same with my self-developed tool, which executes the bin echo affiliate, and the Tetragon does not register the event in that case. I started doubting that my code was right, so I double-checked it. Exec wave is there. Everything should have been registered, but it didn't. I see that if we go through the bash, we do register the event. Then I kill it because we want to prevent its launch, but my tool still did not give me the right results. So I addressed the Tetragon team with this question, and they told me that when you initiate a syscall, you announce your parameters in the user space, and when the kernel processes your request, it copies the same parameters to the kernel space. And if you use this policy, it's not a given that these parameters are copied and pasted in the user space, in the user port. So a primitive way to detect the start of processes does not allow us to register them at all times. And the second example is about the network part. The Tetragon repository has a tool for registering network activities. It registers the source, the destination, all the ports, and even the protocol. So you can use it out of the box on the face of it, but you can bypass it at the L2 level. Well, we can copy and paste the open source code for sending L2 frames, and Coral generates events in Tetragon because it uses 3+, while my tool that uses L2 does not trigger the event registration because it has no network packets. And a couple of words about the symlinks. Tetragon does not resolve them when the process starts. The bin echo is killed according to the policy, while the symlink allows us to go ahead with the process. As for the files, it's just the opposite. I created a symlink for a directory, and then and then the tetragon resolves this event. This is it as far as tetragon is concerned. Now let's move on to KubeArmor. This is a cloud-native runtime security enforcement system that restricts the behavior of pods, containers, and nodes at the system level. It can also use eBPF tools. And that's why I included that tool in my research. Unlike Tetragon, we as administrators do not describe the function, the kernel function that we want to monitor. We just describe the list of processes, files, and network actions, and just pin our hopes that KubeArmor developers will do the rest. Let's take a look at the KubeArmor policy. The KubeArmor def is what we're interested in. Then we start the apt and apt get, and when that happens, we specify in the action what we want to do. We just want to log it, so it's just an audit. The configuration, labs configuration, is very similar to the previous research. Well, we just use KubeArmor instead of Tetragon. By the way, as far as the kernel logs are concerned, you only get logs in compliance with the policies that you describe. But you can also specify kernel logs log filter all, and in that case you will get logs not just registered in your policies, but also those that are registered by KubeArmor by default: launch, read, and some of the network activities. Let's start with large data. As compared to Tetragon, the maximum number of arguments, the maximum size of arguments is limited by 496 symbols, but a maximum is 19. That's shown on the right-hand side. So KubeArmor no longer registers it after 19. However, in the binary, it's better. All 4,096 symbols are registered. Then I wanted to check the map overflowing, and I specified this policy. And actually, I got a little upset because the events were lost even in a limited number of starts. I launched my own tool to open etc password, and overall it was 16 in total and 32 in the second case. Just one event out of 16 was registered, and in the second case only 13 out of 32 events were registered, and I'm going to give you more details as we go. Now let's try to detect the process that we are interested in. We specify the pathway and specify the audit. When we start through PH, everything goes smoothly and KubeArmor registers an event. As you can see, it registers bin echo and its arguments, so the process itself and the tool that it used to detect the event. When I used my own tool, nothing happened. And if you turn off the filter for using events only in your policies, KubeArmor just registers the fact that I started my tool, but it did not register the echo affiliate process. Let's substitute let's replace allow with block, and as you can see, the affiliate echo process did not go through, but Cubommer did not register it. And as mentioned, it uses Linux security model for enforcement. And here you can see the way it created a policy deny bin echo. That's why it was blocked. However, for event registration, it used eBPF, and you might have noticed that the process detection is done with the help of the syscall monitoring sysexec VE. And going back to the Tetragon example, it's not the best function to monitor processes, and that's why the bin echo start event was lost in the process. As for symlinks, it's just the opposite as compared with Tetragon. When we don't see any resolution when we request and read file. This is the TMP password, which is a symlink to the ETC password. And now let's talk about the network part of Cubommer. It allows us to register 3 different types of protocol: TCP, UDP, and ICMP. And it just registers the protocols without using filters on destination, source, and the port. And I specified the relevant policies, for instance, ICMP, TCP, and UDP registration. And the first thing I noticed is that Cubommer registers a socket for all the 3 protocols. It doesn't provide you with any additional information, but you can see the ratio between a socket opening and the payload event. That's 10 to 1. And if the maps are limited and can overflow, it doesn't make any sense to have that. You give an attacker a legitimate way to overflow your maps and rewrite the events. That's why, in case of ETC password, in the previous slides I demonstrated to you a limited number of registered events. So that's why they were lost, because Cubommer registers useless events. So let's go back to the TCP protocol. For this policy, Cubommer uses the TCP Connect for tracing, and it identifies the address and protocol and the port that we use for connection. However, this policy does not allow it to register creation and connection to the TCP link if you act as a TCP server. However, you can still register it by turning off the filter of registering logs through policies. And if you turn off the log filter, you risk overflowing the database, because you risk overflowing the maps because you will receive exhaustive information. As for UDP, Cubommer uses the connect syscall to detect package transmission, but UDP is a connectionless protocol, and syscall is only used to identify the address and the port by default. An alternative would be to use send to syscalls where you specify the address and the destination port. So you use send to program for sending packets and specify the destination address. Then we use strace tool to see that we activated this tool, you specify the port, the address, and then you use netcat to start the server, and everything runs smoothly. And kubearmor does not register it because we did not use the sysconnect to send UDP requests. We only register sys exec VE and so on. As for the ICMP, it registers just the socket creation, but not the address or the destination port, which means that you can send anything safely by ICMP, and kubearmor will not register it. Let's sum up. Tetragon can bypass the traces if you pass invalid UTF-8 characters or run a binary with large path. In case of kubearmor, you can also just run a process. And just running a process is sufficient for kubearmor because kubearmor traces a 6 exec key, which does not register all the events. So the same is true for files, since some of the events were lost. And for the network part, you can, in UDP, you can use the send-to function without using the sysconnect syscall, and kubearmor will not see any UDP packets sent. In case of ICMP, we can just send packets because only sockets are created, and the TCP server will only be detected if you turn off the log filter. As for privileges, I didn't have time to analyze them, but as far as I remember, Tetragon identifies them with the help of Linux security module, and it was outside of the scope of our research. So why we can bypass eBPF-based tools? Because the tools are not properly executed. As I have demonstrated to you, they either monitor wrong functions or only partially monitor the right functions. They lose events because they register too much noise, and coding might be tempered with, but this is not a problem inherent in these tools only. And there are eBPF limitations that because of which we either lose some of the events or cannot provide them with all the functions because the arguments are being cut off. And the human factor. Tetragon is a powerful tool, but we don't come up with the right policies, and that's why we cannot register some things that we would like to register. If you're interested in finding more information, you can use the tools demonstrated in the slide to properly describe the policies for registering various actions, or you can use them for offensive purposes to see how to activate the functions. And this slide shows both CLI tools and kernel Shark, which has a nice GUI. And again, if you want to get additional information, you can scan the QR codes and find additional eBPF resources, bypass researchers on eBPF tools, and just see for yourself how we start the processes in Linux. That brings me to the end of my presentation. I'll be happy to take your questions, if any. Good evening, thank you for your presentation. I just wanted to find out if there are any tools to extend the map memory so that they can register more events. And the second part of the question is, can a bad actor have any impact on the user part to deactivate the kernel space components? Well, as for maps, Tetragon. Well, in Tetragon, you can set the parameters in such a way as to specify the map size and the number of events that can be in the queue. As for the maximum size, I failed to find the relevant information when I developed programs for eBPF. They were banned by the verifier that uploads them into the kernel part. If the size was just over 200 kilobytes, but Tetragon can register more events, and you can even specify it with the help of the arguments. You can specify the size of maps with the help of arguments. What was the second part of the question? Can a bad actor have any impact on the kernel rules via user space? Well, I once came across a research online that read that an attacker can modify the maps used by the developers. So if he injected an invalid configuration, he could force maps not to register events at all. This is the only case I know of. Thank you for your presentation. My question is as follows. In the case you mentioned that if you initiate lots of processes simultaneously, have you tried to compare it with the audit T? Will events be lost in that case? Well, I did not compare it with the audit D, and actually I'm not familiar with it.